Look down at your feet. The ground feels solid, like it has been sitting there, perfectly still, forever. Until a sudden vibration shatters the illusion. You are actually standing on a massive, cracked puzzle piece, and that entire piece is floating on a sea of churning hot rock. Because those massive puzzle pieces are constantly shifting, our planet undergoes roughly 500,000 detectable earthquakes every single year. The shaking happens when these massive plates attempt to slide past one another, only to find themselves physically locked in place. To understand why that stuck rock eventually breaks free with such terrifying violence, we have to leave the surface behind and travel hundreds of miles underground. Deep beneath our feet, massive slabs of rock push against each other. Because their edges are rough, friction locks them together, preventing them from gliding past one another. As the plates keep pushing, enormous pressure builds up. The rock holds the stored energy, straining more and more, until it violently snaps. The exact point in the deep rock where that physical fracture occurs is called the hypocenter. This origin point can be located as far as 450 miles straight down into the Earth. That's deeper than 1,500 Empire State Buildings stacked end to end. If the physical rock is breaking hundreds of miles beneath the surface, how does that deep subterranean snap manage to level human structures all the way up top? If you travel in a perfectly vertical line from that deep underground break straight up to the Earth's surface, you hit ground zero. We call this specific surface bullseye the epicenter. When a news report says the epicenter was in a specific city, it means the city was sitting directly above the deep underground blast zone. The destructiveness of a quake relies on the distance between that deep hypocenter and the epicenter. When the snap is extremely deep, the Earth absorbs most of the shock. But when the snap happens close to the surface, the ground cannot cushion the blow. When the rock breaks, it releases all its pent-up energy outward through the crust in the form of seismic waves. These are literally sound waves traveling through solid rock. All that stored tension instantly converts into a kinetic shock wave, blasting outward from the point of the break. The first to arrive are the primary waves, or P waves. They rip through the deep rock at speeds up to 15,000 miles per hour, compressing and expanding the ground in a rapid forward motion. Hard on their heels come the secondary waves. S waves travel slower, but they are the true troublemakers, whipping the ground side to side and up and down. Animals can often feel those fast-moving P waves, causing dogs to bark seconds before the S waves arrive to buckle streetcar tracks and tear apart infrastructure. The energy ripping through the crust is staggering. A magnitude 9.0 earthquake releases the equivalent energy of 32,000 atomic bombs detonating all at once underground. This heavy metal physics event presents an immense, unstoppable wave of kinetic force that our surface cities are forced to face head-on. We have no way to stop massive tectonic plates from shifting, and we cannot accurately predict the exact moment friction will fail and cause a snap. This scientific seismograph reading shows exactly how humans have historically recorded and measured this erratic, violent energy after the fact. But instead of continuing to build rigid structures that try to fight against those incoming S waves, human engineers decided to adapt to the motion. Modern architecture now incorporates giant internal shock absorbers and heavy swinging weights. This allows skyscrapers to safely sway and move with the earthquake instead of snapping against it. An earthquake is the planet stretching its muscles. By decoding the exact specific mechanics of that deep underground snap, we have now learned how to survive the dance.